Before going to further representation theorem, let's answer a question which was posed right before the break. Is U unique? It is interesting indeed because I choose the sequence 1 minus 1 over n to go toward the boundary. And even from that sequence, I took some subsequences. Somebody might take other subsequences, or even from the very beginning, it starts from another sequence. So at the end of the day, do we arrive at the same function? The answer is yes, and there are two ways to answer this question. One, which was the uniqueness theorem that we saw yesterday. If U is represented by 1 over 2 pi integral of PR. I don't write the arguments, I mean, just to explain what happens. But by the integral of P1 and at the same time by the integral of U2, then we see that integral of PR U1 minus U2 is equal to 0. And yesterday we saw two uniqueness theorem, and one of them was precisely this one, even in more general format. So the uniqueness theorem says that U1 minus U2 is identically 0. I remind you the theorem, recall. The theorem said that if integral of PR d mu is 0, then mu is identically 0. Even for a measure, this is an absolutely continuous measure, but even in the general case, if we consider a measure which might have the singular parts, but its integral with respect to p is 0, then mu has to be 0. So that's the uniqueness theorem we saw yesterday. That's one way to do it. There is another way, which is still it's an interesting result and lies deeper. It says that if you have such a representation, I mean, I write this in detail because an important theorem of Fatou. If U is given by a Poisson integral, T dt, and even let me to give you the most general setting, not just the way I wrote here is a measure which is absolutely continuous. The general case, they put 2 pi with t here. That's good. This is the absolute part that we have, but it might also have a singular part. So I add here plus d sigma e to the it. You know that any measure can be decomposed in this way. So in other words, I put a measure d mu here, but instead of writing d mu, I did it more explicitly. I did the decomposition with respect to Lebesgue measure, the singular part and the absolutely continuous part. And then Fatou says that lim r goes to 1, u r e to the I theta exists and is equal to the little one almost everywhere on T. And we cannot do better than that. The limit exists is equal to the absolutely continuous part of the measure. It answers our previous questions because here, if u is represented by a Poisson integral of u1 and also Poisson integral of u2, when we go to boundary with capital U, the limit is equal to u1 and also is equal to u2 almost everywhere. So u1 has to be equal to u2. That is why we recover uniqueness from this theorem. This theorem is more important than what we used here, but still it answers the question you wanted. Now I share another file. Because time is running out, I explain on the file. Share this one. And we go. This is the PDF file that I shared with you. And what we covered in the first part today was this one. We started with, it's better to, it's like I will not be able to write on this PDF file. But I can explain on the screen. Let me see, maybe I can stop sharing. I can open it with another surface so that I can write on it. Open with Microsoft Edge. Okay, now I can write. That's good. So what we did today, construction was yesterday. Still convergence, and yeah, Poisson representation. This is what we did today. We started with h of d bar and then h infinity. The main ingredient, L infinity, is the dual of L1, and L1 is separable. You saw this rather long proof. And now pretty much we copy paste the same thing for HP. And this time we use the fact that LP is the dual of LQ and LP is separable, precisely the same. And there is a reason I didn't write P bigger than or equal to 1 less than infinity. I separated the case 1 from this one, which is strictly bigger than 1. And that is lies on the very, very deep result of Riess brothers. So, but this proof is precisely the same proof as we saw before, except that we work with LP and LQ. Nothing is more special about this. So given a function in HP, then there is, again, something exists. And this gives us by Riess theorem, by duality, a U in LP such that we have the Poisson representation and the norms coincide. The same strategy as before. And why the same technique does not work in Liddell H1? The reason is that L1 is not dual of something. It's not something trivial. It's a theorem, and even there is a research paper on this. But at the end of the day, L1 is not a dual space. That is why this technique is not working if we copy paste for L1. So what is the remedy? The remedy I explained on the first day. Instead of considering L1 by itself, we put it in M, in the space of measures. And the good thing about M is that M is the dual of C. So this is a dual space, but L1 is not. And now everything works. The only shortcoming is that in the previous case, when we are in HP, the function we obtain is in LP. The theorem before, U was in H1, U was in H infinity, little u was in L infinity. Here, if we do the same and apply the contour diagonalization, the limiting object that we obtain is not necessarily a function in L1. It can be a measure. In other words, we can have a sequence here, but it converges in our topology to something which is a measure. The picture doesn't say it. The way I draw the picture, it suggests that L1 is closed in M with respect to that topology, but that is not the case. We can have a sequence in L1, but the limit be a measure outside the set of. And the consequence of this is here. We have a U which is in H1. When we do the limiting process, what we obtain at the end of the day is a measure. So U is given by the Poisson integral of a measure, and well, we have the norm identity too. It is interesting to know that we cannot do better than this. And the best example is indeed the Poisson integral itself. If you can see the U to be 1 minus R2, 1 plus R2 minus 2R cos theta, it satisfies this property. And when you take the limit, when it goes to the boundary, and what happens when R goes to 1, something very interesting happens. Here is the point 1. At all these points, except 1, when we go to the boundary, little u is equal to 0. And at the point 1, little u is equal to plus infinity. So at just one point, the limit is plus infinity. At all other points is equal to 0. So if we apply the Lebesgue integration theory and try to recover capital U from a small u, it doesn't work. Any integral with a small u would be 0. So the previous representation with little u doesn't work. And we see here precisely the measure mu, which represents this capital, is the Dirac measure anchored at point 1. So the result is optimal. We cannot do better than that. Another thing which comes from this theorem is that if we consider positive harmonic function, when we do the subsequence and the limiting process, everything is positive. So the measure we obtain at the end of the day is also positive too. And this is a special case of the previous result, but by itself it is important. It is called Herklot's representation theorem. If you have a positive harmonic function, which automatically satisfies the restriction we are looking for, so positive already means that this is in H1. There is a measure, but more than that, the measure is positive. and U is represented by a Poisson integral of a positive measure. A little bit of work with the Poisson integral. We obtain a very important theorem in potential theory and harmonic analysis. It's called Harmonic inequality. If U is positive harmonic function on D, U at every point is controlled by U at the point 0 with some coefficients which depends on the location of the location of U r e to the I theta. And this is very easy to prove because the Poisson kernel is positive and upper bounded by 1 plus r, 1 minus r, and lower bounded by this, and we immediately obtain the result. What is important in Harmonic inequality is that if you have any other connected domain, for example, something like theta, I mean, it cannot be, it's not necessarily the unit circle. And you have a positive, I cannot change the color, doesn't matter. And you have a positive harmonic function on this. Then pick a point here, put it Z. And another point, I mean, in other part of the domain, for example, W here. What Harmonic inequality says is that U at point Z over U at point W is upper bounded and lower bounded by a constant C. And the important thing is that C does not depend on U. Of course, C depends on Z and W and also the shape of our domain omega. This is okay, but it doesn't depend on U. Uniformly, the word I emphasize on uniform. Uniformly for any positive harmonic function, U of Z is controlled by U of W and vice versa. That's the essence of Harmonic inequality, which has many, many interesting applications. And the proof is precisely based on this corollary, because you can connect your Z to W by a piecewise linear curve like this, which is away from the frontier. And then this is a standard in complex analysis. And then cover this by a finite number of disks. And on each disk, you apply this inequality. And then you go from beginning to the end, you obtain what you want with some C, which, I mean, would depend on Z at W, but not at U. The representation, to finish this section, the representation we mentioned here were for harmonic functions, either real or complex. So they work for capital H2 because capital H, I mean, being holomorph is also harmonic. So all the representation before also works for Hardy spaces, the analytic one. We can say a little bit more. Yes, for example, here, if F is in HP, there is a function in LP such that this representation works. We saw it before, that's good. Or we have this representation. But now consider the fact that F has to be analytic. And being analytic, when we calculate the Fourier coefficient, half of the spectrum is 0. This is the meaning of being analytic. So we have the same representation, but N, instead of starting from minus infinity to infinity, it starts from 0 to infinity. So the function which is here, it is true that it lives in LP, but it's a special subclass of LP, the subclass whose negative spectrum is 0. And that is why in pretty much all books about Hardy spaces, they call this subspace HP of T. HP means a subclass of LP, but half of the spectrum is equal to 0. So all the theorems we mentioned can be, summarized here. And still you see I didn't write P equal to 1, even though it's true. But without any effort, all the previous theorem putting together implies this one. And also for this, the same one for H infinity. So even for P equal to infinity, no extra effort is needed. What is very fundamental, and I didn't go through the detail in the proof here in the PDF file, but it's available in the book, is that if you modify the representation we have for little h1, you obtain a representation for capital H1 as this. This is correct. There is no mistake in it. But that's not the whole truth. The whole truth is obtained by theorem of Rees brothers. If you have a measure such that half of the spectrum is 0, here is the negative part because we are working with analytic functions, then the measure has to be absolutely continuous. It's really, really beautiful theorem. And that is why instead of mu, we can write here f star dt. And well, the sum starts from 0. We know this. The real difference is here compared to this one. So from here to there is the theorem of Rees brothers. And that is why in this theorem, which is a summary of all of the previous results for little h1, but written for Hardy spaces, even we can put less than or equal here and less than or equal here, as long as this representation is concerned. So the analytic part brings us a very solid representation theorem for all cases. Of course, we do not expect to have such a representation for p less than 1, because even the Lebesgue integral is not well defined. So that finishes our studies of representation theorems as long as Poisson integral is concerned. There are some other representation which I mentioned, and there is a section here which I have provided a list of all of them for further reference. In the 30 minutes remaining, I go to something which I promised on Monday, equivalent definition of Hardy spaces on D for the spatial case P equal to 2. But when we want to generalize, sometimes it works, sometimes it does not. So here it is, H2, yeah. 4 different ways to define H2. Hardy space H infinity, the definition is easy. You say that the norm infinity is the supremum, and here is the Hardy space. So it's the simplest way of defining a norm, but many difficulties are ahead. And indeed, H infinity proved to be a challenging space. And there were some problems like corona problem, which were open for many, many years and finally was settled by Carlson. And still in the several variable case is an open question. We have a session, if I'm not mistaken, week 13 or week 14, on corona problem. So it's a corona problem on H infinity of D, and there are many progress on this topic. So I mentioned this just to say that even though the definition of norm is easy, but many challenging problems are about bounded analytic functions, even in the open unit disk. In the several variable, it's still open. The next step is to go into H2. Why H2 is interesting? Because at the same time, it's also a Hilbert space. And we can use the techniques of Hilbert spaces to deduce result about H2. Here I mentioned 4 definitions, and we see what are the consequences of each one of these. The first one is by Taylor or Fourier coefficients. You consider analytic functions for which Taylor coefficients are square summable. Naively speaking, we say that H2 is equal to little L2. That's what we say. So that's a norm. It's very easy because it's a norm on L2. And one thing which is essential here is that even though this is one way to define the norm on H2, but if you want to generalize, that is not a good formula. If you put here, spaces such that the sum A and P 1 over P is finite, and say that I want to consider these spaces, this is not HP. It's a space which is called LP of A. So generalization is possible, but it does not give us the Hardy space. It gives us something else if P is not equal to 2. That is why we forget about Taylor definition by Taylor coefficients. We use another way. And the second way, these are some explanation about what's going on, and even LPA mentioned here. There is a book on this subject, very recent one. So that is why we forget about the previous definition. We go to another one. By integral means, open unit disk, we consider circle of radius r between 1 and 0, and then we calculate the average of f on this circle. And by Parseval identity, this integral is exactly equal to this one, because the Fourier coefficient of fr are an times r to the n, and so here you obtain this formula. And if we take the supremum and even the limit with respect to r as r goes to 1, we obtain the same combination that we had before. So this suggests that another way to define the Hardy space H2 by this formula. We calculate the averages on the circles, and then we take supremum r between 0 and 1. And in this case, if you replace 2 by P, we obtain Hardy classes HP. So that is a good way to define Hardy spaces. Okay, good. More definitions. Another definition which is very useful in the application, in particular when we consider composition operators, is by the harmonic majorant. An observation: if there is a harmonic function u such that absolute value of f squared is controlled by u, is less than or equal to u, and then now we fix radius r and we integrate. This is the integral that we want to show it's bounded. And the good thing about harmonic function is that the average on the circle of radius r is equal to the value on the center. Very good. Doesn't depend on r. And therefore, it's in Hardy spaces. Conclusion is that f is in the Hardy spaces, and even we have an upper bound based on that harmonic function. So the norm is bounded by the root of u at point 0. Now we go the other way around. If f is in H2 is given, then we have the Poisson integral. We saw this before. We have this. And now you apply either the Holder inequality or the Jensen inequality with phi of t is equal to T2, which is a convex function. You obtain this inequality. That's a consequence of either Cauchy-Schwarz or Jensen inequality. And this part gives you a function u. So we obtain, this is the u I mentioned, and u at the point 0 is precisely the norm of f star on the boundary squared. And we know that that is equal to the norm of f in H2. In other words, if you put the first and the second part together, the norm of f is given by this formula. We consider all the harmonic majorants, evaluate them at 0, and then take the infimum. The infimum is precisely equal to the norm of f squared. So that's another way. As I said, it is a good way to look at H2 and use the harmonic majorants for example, for composition operators. It works also for P. That's a good way. So here, if we replace 2 by P, it works. That's so as long as definition 2 and definition 3, which is this one, as long as generalization are concerned, both of them are good. We can replace 2 by P and obtain something. There is something in the chat. No, the majorant, someone asks, is this majorant is unique? Of course not. For example, if U is a majorant, U plus 1 is also a majorant. So the majorant is not unique. And but you can ask, is the best majorant, the least one, is unique? Now the answer is yes. The least harmonic majorant is unique. There is a little bit of work to show that. So as long as we want to go from 2 to P, that's okay. One comment about definition 2 and definition 3. When we go to the upper half plane, well, here choices of circles of radius r is very natural to do. To do it and obtain our definition. What about the upper half plane or right half plane? The engineers like the right half plane. Another question. Yes, I answered when we go to the upper half plane, well, if we consider circles, it's not clear where the center should be. And also, if the center is big, we go outside the boundary. So circles are not natural for the upper half plane. For the upper half plane, since R is the boundary, it is natural to consider lines like this and take the means on these lines. And if the mean are uniformly bounded, we define HP of C plus to be those functions. This is good. That's the way we define Hardy spaces in the upper half plane, either HP or H2. Keep this in mind. Come to the definition 3. So that's another way. So we say, okay, let's go to the upper half plane. And here, well, we consider all functions such that norm of f is less than or equal to u. And then we define the norm by the same remedy we have here. That's good. It gives us a Hardy space, HP of C plus. It is interesting to note that this Hardy space is not the same as this one. And that is why in some books they write it this way to show that this is not the same Hardy space. So we obtain a Hardy space, but not the same as before. Be careful going from disk to upper half plane. It works. It is, gives the answer in many cases, but there are at least 2 classes of Hardy spaces in the upper half plane, and which are not the same. What makes us more confusing is that the Poisson integral works here. The Poisson integral also works here, but they show different things. So be careful which Hardy spaces you use in the upper half plane and which definitions you use. Finally, the last one, which finishes our courses, it's an interesting formula. Indeed, this is the formula that yesterday Joe Sima asked about it by a private message, and its generalization to the case P. If for the case P equal to 2 is the simplest one, just consider this integral in which dA of z is simply dx dy, is this area integral. F is given, you have f prime, you have log, and simply plug in the formula and use Parseval. From here to here is the Parseval identity. And then everything is positive. You can change the order of summation and integral because everything is positive. And if you do this, you obtain the sum from n equal to 1, not 0. From n equal to 1 up to infinity an, and this is precisely f minus 0, its norm in H2. And that is why we have this very beautiful formula for the norm. But note that in definition 2, we had just line integral, and here we have a double integral. Even though I wrote integral over d, it's indeed integral. It's a double integral. Sometimes people write it this way. If you put 2 integrals, it's more honest that it's an area integral. So that's one way to give the formula in H2 by an area integral, and this can be generalized. The formula is a bit more complicated to obtain a formula for f minus f0 in HP squared. There is a formula, and let me write the formula. Oops. It's P2 integral over d fz. Don't know what, something is wrong. Exponent p minus 2, f prime z exponent 2, and log of 1 minus z daz. I remember this because Joe asked me yesterday, and I went and looked at the literature and find the formula. So here it is. Here, because of the presence of f of z to the exponent p minus 2, which might be a negative exponent. For example, consider p equal to 1, and that's the case which is needed indeed in the proof of Corona theorem. We obtain f prime squared divided by f. And if f has zeros, there are some difficulties. That's why in this formula, there are some more restriction. Here, there is no more restriction. I mean, just f in H2. Here, f is in HP, but two more restriction. F has a simple zero at the origin at most, in which case this becomes 0, and f has no other 0. There is a comment, let me see. David Bletcher. Oh, hello, David. I didn't know you are here. Javad, can you post the link to the game, please? Sure. Okay, sure, David. We need to assume that f has no other 0 because there is a problem here. It will not work. But having a simple 0 at the origin is okay. We can compare with that. And the last thing, sometimes working with log of 1 over z is a bit difficult, but as z goes to the boundary, log of 1 over mod z is pretty much the same as 1 minus absolute value of z. And so we ask what happens if we replace log of 1 over mod z by 1 minus absolute value of z, or absolute value of z square. Square is not really important because we can write 1 plus 1 minus, and 1 plus doesn't do anything. It's a good substitution here. It doesn't give us precisely the formula we wanted, but it gives almost the same thing. The same technique, I mean, we write f prime, that's the definition. From here to there is Parseval identity. And then everything positive, we change the order of summation and integral. You see, it doesn't completely simplifies. We have a factor of n over n plus 1 here if we use 1 minus mod z2. The good thing about logarithm was that when we evaluate this integral, everything simplifies, and what remains is just mod a n squared. With 1 minus z2, even though it's nicer, but the penalty is paid at the end. We have n over n plus 1. Not that bad, because when n goes to infinity, n over n plus 1 goes to 1. And that is why we can obtain an upper and lower bound. The upper bound is 1, lower bound is a half. So this quantity, which is the same as this one, is controlled from above and from below, both sides, by normal f minus f0. It's not a complete identity, but still this formula is very useful. Well, I explained when I talk about H2, how it goes when we go to HP. Briefly speaking, for case definitions 2, 3, and 4, it works if we replace 2 by p. In the first definition, it gives us something else. And even if we go to upper half plane and we replace 2 by p, we obtain different spaces, and we need to be careful. Well, that's it. It finishes 6 hours of lectures about just representation theorems. Ryan asked, Are the definition of complex RD space in terms of maximum? Yes, yes, yes. You said it based on definition based on this. It's not that honest to say a definition. These are deep theorems, which says that, yes, something is in the Hardy space if we consider the maximal function on the boundary, which I didn't give even the definition, and this function is in L1. It's a deep theorem. But that theorem can be used and has been used by experts to define Hardy spaces of in Rn. So in a sense, the answer to your question is yes and no. Yes, because we have an kind of if and only if, and when we have if and only if, we can adopt as a definition. No, because in no books about the classical setting, this is given as the definition for D. It's a theorem for both cases. And David asked me to share the PDF file again. Now I have to find the chat. Okay, I go. Main chapter Hardy spaces. Here is the PDF file, but I mean, it will be modified further and I mean, reorganized, and the final version will be available too. Shabnam asks how these multiple definitions of Hardy spaces came to existence. Well, how they came into existence. I do not know really how to answer this question, but at least it's in line with what Ryan asked and my answer to Ryan. When we want to generalize, when we want to go either from 2 to P, or from disk to upper half plane, or even to Rn and Cn. Which definition do we use? And this is precisely the point. We have, if we add the two also that mentioned by Ryan, we have 6 or 7 equivalent definition for the Hardy spaces on the open unit disk. And when we generalize, each one of them gives us spaces which do not necessarily coincide. That is why we have multiple definition in the open unit disk. But I need to think more about this question, how they came into existence. I need to think more about it.
Thank you.
Thank you, indeed. So next week, we will come back with a mini course by Professor Ransford on Dirichlet spaces. We will have 6 plenary talks and also a colloquium talk, if I'm not mistaken, by Sasha Wahlberg. So, I think it's by Sasha. Let me double check. I have the schedule here. Week 2, yes, the colloquium talk is by Sasha Wahlberg, a mini course by Tom Ransford on Dirichlet spaces, and we will have 6 plenary talks on Dirichlet spaces by, in the order of the program, by Partington, Zhu, Benetto, Arcusi, Poliasis, and El Fella, and also 2 contributed talks by Idrisi and Co. I mean, program, in a sense, starts next week, and hope to see you all on Tuesday morning.